Let's start with the main point. Online research crowdsource platforms allow a huge number of global participants to contribute to research studies. This allows large-scale researches to complete online while saving time and resources. This is a missed opportunity because we don't give participants feedback about how well they do. So, for this MQP, we would like to focus on two questions. First, how might we design feedback as part of a visualization study? And second, does feedback lead participants to different experiences or performance in such studies? When we talk about data visualization, we have to mention these people because their researches are the backbone of modern data viz experiments. First, we have to mention Cleveland and McGill's famous graph perception experiment. This image shows that human has the highest accuracy to identify position along a common scale, while having the least accuracy to identify color, saturation, and shading. This project recreated Cleveland and McGill's study on comparing two areas of different types of graphs. Going back to the timeline, in 2010, Here and Bostock conducted a large-scale experiment which included about 1,600 people to verify the quality of input came from Amazon's Mechanical Turk, an online research crowdsource platform. In 2013, Howman, Adar, and Shah again used Amazon's Mechanical Turk to test how social conditions might give anchoring effects but might not necessarily increase the error percentage. In 2014, Harrison, Chang, Frankenery, and Young used the inferred Weber models to produce a perceptually driven ranking table by just noticeable difference value. Thanks to these studies, our project has the valuable information needed to design a data visualization experiment. However, none of these studies have explored the usage of feedback within a data visualization assessment. We looked at feedback from different types of educational softwares and platforms such as Udemy, Lynda, ClassDojo, Labs in the Wild, and Duolingo. Not limited to educational applications, we gathered feedback samples from video games and fitness apps as well. From all the feedback samples, we summarized the 4 design principles for a feedback page. Firstly, in writing, the feedback should be an affirmative influencer which the user wants to improve his or her performance in order to get positive feedback. Next, repeatability. There should be a repeating occurrence of feedback, where the user consistently receives the feedback after a certain amount of exercise. Next, coherence. The content of the feedback must relate to the context. Coherence is imperative to avoid confusion while assisting users to improve their performance. And last but not least, data-driven. The feedback has to be objective and real. We used Prolific as our crowdsource platform. After signing up for the study, users could access to our website with their worker ID. There are altogether 20 sets of 20 problems, which are 400 problems in total. Each set contains questions about bar charts, bubble charts, pie charts, and stack bar charts. Users were given 5 questions for each graph type in one set. Users are asked to complete at least 2 sets of questions, and then can either quit the study or proceed to the next set. Half of the participants were given feedback after each set, while the other half received no feedback. Users received 3 types of feedback. First, how well they did on each trial. Second, a graph of distribution of errors. And third, donut charts for each chart type. After users finish their desired number of question sets, they need to complete a survey which contains some opinion and demographic questions. Now, let's take a look at the data we gathered from 64 users. This first graph is a scatter points diagram where each point is the difference between users' judgmental error across the number of sets. We can see the highest number of sets completed by users were 10 sets, and this particular user was in the no feedback group. To focus on the majority of the users, we generated graphs for users who completed less than or equal to 5 sets. We then applied a linear smooth fit to see the learning curves of users over time. Like we expected, in average, the feedback group improved slightly faster than the non-feedback group. it is interesting to see that among the 4 graph types, pie charts have the most differences between the 2 groups' learning curves. On the other hand, there appears to be no definitive learning curve differences for stacked bar charts. These data can be summarized to 2 points. First point, feedback influenced the user to learn accurate data visualization reading faster. Second point, with feedback, users were more confident to stop practicing data visualization questions. Data visualization online assessment should consider incorporate more feedback because feedback can help users to learn graph literacy faster. This can help researchers to collect optimize the user performance, thus lead to more comprehensive analysis and results.